All right, now that we have seen some examples of limits, let's see some non-examples. So specifically, let's think about the limit as xy goes to 0, 0 of 2xy over x squared plus y squared. Now, in this case, I didn't tell you that the limit exists or what it's equal to. So we need to investigate a little bit as to what this limit might be if it does exist. So one way to do that is just to think about different ways to approach 0, 0, where we're trying to limit, in a way that we can clearly understand. So let's think about approaching 0, 0 along the x-axis. So that is, I'm not going to worry about all points that are close to 0, 0. I'm just going to look at the points that are close to 0, 0 and on the x-axis. So the nice thing about that is that those are the points where the y-coordinate is 0. So this expression, 2xy over x squared plus y squared, now just becomes 2x times 0 over x squared plus 0 squared, which is just 0. So all along the x-axis, this function is identically equal to 0. So if the limit exists, then it must be 0, because arbitrarily close to the origin along the x-axis, the value of this function is 0. But if we approach along a different line, so let's only look at points where the x and y coordinates are equal, then what is this expression? 2xy over x squared plus y squared? Well, if x is equal to y, then that becomes 2xx over x squared plus x squared. Well, that's just 2x squared over 2x squared, which is 1. Which means that along the line y equals x, this function is identically equal to 1. So since approaching the origin along one line we get 0, and along the other line we get 1, it must be the case that this limit doesn't exist. Now you might wonder what this thing could possibly look like. Let's take a look at the graph. So here is a picture of the graph. And you can see that as you approach along this line, so this is the line y equals x, the function is identically equal to 1. Whereas along the x-axis, although it's hard to see, along the x-axis, the function is identically equal to 0, as it is along the y-axis. So in this example, you can see from the graph some strange behavior near the origin that clearly indicates that this limit will not exist. And that's exactly what we see with this calculation. So let's look at another example that's even stranger. So let's think about the limit as xy goes to 0, 0 of xy squared over x squared plus y to the 4th. And again, I did not say whether or not this limit exists, so let's investigate. Let's approach the origin. Now let's just write down along an arbitrary line. So every line through the origin looks like y equals mx, or possibly x equals 0. That also will fit into this, but let's just look at this this line. So y equals mx. In this case, we replace y with mx everywhere, and let's think about the limit now as x goes to 0. So as x goes to 0, we're approaching along this line, we're approaching the origin. So what do we get when y equals mx? Well, the numerator becomes m squared x to the 3rd. The denominator is x squared plus m to the 4th x to the 4th. We have a factor of x squared in both the numerator and denominator. We factor that out and we get this. And what happens as x goes to 0? Well, the denominator is bounded away from 0. It's always greater than or equal to 1. And so the numerator, which is going to 0, dominates, and we get a limit 0. So this means every possible way of approaching the origin along a line, we see value 0. So certainly, it seems like the limit should be 0. But let's see what happens if we approach 0, 0 along a different curve, not along a line, but let's look at what happens if we approach along the parabola. So we're going to do the same kind of analysis that we did here. Everywhere we see an x, we're going to replace it by a y squared. And then as y goes to 0, we are approaching 0, 0 along this parabola. So everywhere we see an x, we replace it by a y squared. So this x squared becomes y to the fourth. And the limit as y goes to 0 of this, well, that's just y to the fourth over 2y to the fourth. So that's just a half. It's constantly equal to a half, right? The y's cancel, and I just get a half. So if I approach 0, 0 along the parabola, x equals y squared, I get 1/2. So we can also take a look at what this graph looks like. And here you can clearly see that if I look at the parabola, so I tried to picture the parabola here. Here is what the graph looks like above the parabola. So the graph is at a constant height, 1/2. And it's not so easy to see, but if you approach along any line, what you'll see is that you will always limit to 0. Okay, so what do we learn from all of this? Moral is, you can prove that limits don't exist by approaching along different curves and finding different limits. So if you're trying to see that some limit doesn't exist, you might think about different ways to approach the point in question, that is, different curves that go through that point. And the advantage here is that by approaching along a curve, you're effectively writing down a limit of a function of one variable, just as we did here. So by approaching along these lines, we were able to turn these limits into limits of a function of one variable. So if you can find two curves where you get different limits, then the limit can't exist. It's also important to point out that you will not prove that a limit exists by showing that if you approach along different curves, you get the same limit. That was this last example where we approached along all the different lines through the origin, and we got the same limit, and yet the limit didn't exist. So if you ever try to prove that some limit exists by showing that as you approach along various curves, you get the same limit, you're probably headed in the wrong direction. All right.